Yeah, there is.
I mentioned the eraser would be black chalk.
That's how you reset it.
So once the board gets so white, you have to write the white chalk.
And then when you erase the black chalk, it turns the board back to black.
Yes, this all makes perfectly good sense. All right. So what's going to happen?
Took it right off.
As much as it does any of the other chalk.
It's like it's the permanent.
All right. So that's weird. It actually kind of caught some of the eraser chalks and turned it white. Actually, yeah, weird. Alrighty then. So let's integrate both sides of that relation over there. Yay! So integral cosine squared y dy is k over 2 integral of dt, multiplying both sides by dt and integrating. Turns out that cosine squared y integrates to y over 2 plus 1/4 sine 2y. So that's equal to k over 2 plus c. C again is an integration constant. And so in order to evaluate C, we again use our initial condition that for our parcel, r was equal to r naught, this time when t is equal to 0. Last time we put it in terms of the velocity, now we'll put it in terms of r equals r naught when t is equal to 0. Since r is equal to r naught, well, that implies from our definition of theta, theta is 1, because theta was r over r naught. Theta is equal to 1. And that implies y is equal to 0, because cosine squared of 0 is what gives 1, right? Cosine of 0 is 1, so cosine squared of 0 is 1. So y is 0 in order to make theta equal to 1. So y is 0. And then that gives us 0 plus 1/2 sine of 2 times 0, or 0 plus 0, right? Because sine of 0 is 0. So, and then if t is equal to 0, that's also 0. So in other words, c is equal to 0 is what comes out of all this. I'll make that explicit. 0 over 2 plus 1/2 sine of 2 times 0 is equal to k over 2 times 0 plus c. Conclusion is equal to 0. So our solution then is multiplying through by 2 over here. Our solution is that y plus 1/2 sine, this was supposed to be a 1/4 out there, sorry. Something wasn't working out there, that's a 1/4 right there. So y plus 1/2 sine 2y is equal to k times t. That's our implicit solution for how the radius of the cloud varies with time. In other words, what this tells us is if you know y, value of t, right? This is essentially t is a function of y. It's not y as a function of t, it's a transcendental equation. So this is really giving us t as a function of y. It's still useful. You could use a computer to do an inverse lookup kind of thing, or to make a table of y versus t, and then ultimately r versus t. So in other words, we can add where y, which is the inverse cosine of the square root of theta, or in other words, the inverse cosine of the square root of r over r naught, implicitly gives r as a function of time. So we weren't able to solve for r as a function of time. We didn't even really solve for y as a function of time, but we do have an expression for time as a function of y. And in a computer, you can easily make a table of t values and corresponding y values, and then you could make a plot that would then be y versus time, is what it comes down to. And then from that, you could calculate what r was and make a plot of r versus time. So it's, do it, it's just an implicit solution. Expression, we can find the free fall timescale. By setting t is equal to the free fall timescale when the radius has gone to 0. How long does it take the cloud to shrink down to a point? Which won't really happen because then it would need to turn into a black hole without turning into a star first. But the free fall timescales, how long would that take if the pressure didn't rise because the cloud became optically thick and it turned into a star instead? And in fact, the cloud starts out much bigger than the final radius, and so essentially this would be close to how long it takes the cloud to collapse before it becomes optically thick. The free fall timescale by setting t is equal to TFF, T free fall, when r is equal to 0. So if r is equal to 0, what's theta? Theta was r over r naught, so 0. And if theta is equal to 0, what's y?
0?
No. Remember, theta was cosine squared of y, so we need a y such that the cosine of y is equal to 0. When is cosine equal to 0? It's equal to 1 when y is 0. It's equal to 0 when y is equal to, for the first time, it becomes 0 when pi over 2, right? Pi over 2. So y is equal to pi over 2. So our generic expression was that over there, y plus 1/2 sine 2y is kt. Let's plug in y is equal to pi over 2, and t is equal to t free fall. So pi over 2 plus 1/2 sine pi, because it's 2y inside the sine, and y is pi over 2. Pi over 2 plus 1/2 sine 2y is equal to k times the free fall time scale. What's the sign of pi? 0, right, 0. So the free fall time scale is just pi over 2k. But k was defined to be the square root of 8 pi over 3g rho naught. So, more explicitly, the free fall time scale is pi over square root of 32 pi over 3g rho naught. If I want to multiply 2 inside the square root, I make it a 4 times the 8 is 32. Or in other words, our final result is the free fall time scale is equal to 3 pi over 32 times 1 over g rho naught to the 1/2 power. You get a similar expression in the homework. Looks a little bit different because the number out in front is different. That's what it comes down to. You'll get something where it's a different number besides 3 pi over 32. And that's because you made the simplifying assumption that the acceleration for a parcel stays constant as the cloud collapses. That's not right because the gravity is getting stronger and stronger, so it's actually the collapse, the acceleration is getting bigger and bigger. So the cloud actually collapses faster than the simplifying assumption that the acceleration stays constant would imply. Okay, any questions? So notice that there's no R dependence here. All it depends on is the gravitation constant and the initial density of the cloud. There's no reference to where the parcel initially was in the cloud. So you get the same result for every radius within the cloud. It doesn't matter where the parcel started, it takes the same time to fall into the center. And we assume uniform density here. That wouldn't be true if the density were not uniform, but for uniform density, in other words, everything hits the center at the same time. And that's what we mean by a homologous collapse. Everything would hit the center at the same time. Notice, and again, this has connections to cosmology. The Big Bang is the idea that everything's expanding, right? And if you run the clock backwards, everything falls together into a singularity at the same time, the moment of the Big Bang. So this is like the Gnab-Gib. This is running the Big Bang backwards. And yes, people say Gnab-Gib for if the universe eventually ends in a quote-unquote big crunch where everything falls back together. Another name for that is the Gnab-Gib, which is Big Bang spelled backwards, yes.
We're afraid of one term.
We are, as a matter of fact, yes. I think that's actually kind of fun. All right, so note that TFF is independent of R.
That's what you get for calling it the Gnab-Gib.
I know. Wow. The universe does not appreciate the universe.
I dare you make fun of my name.
Yes. Note that TFF is independent of R. Independent of R. So all parts of the cloud take the same time to collapse and the density increases at the same rate everywhere. homologous collapse. I like that word, which is why I always have to say homologous. Homologous collapse. So let's note that our cloud may well be centrally condensed, denser towards the center. And that means that the freeze fall timescale is going to be shorter in the inner part of the cloud than the outer part of the cloud. So in other words, the central regions will collapse and become denser faster than the outer regions. But that would be more typical actual behavior. If the cloud starts out centrally condensed, it's denser towards the center. The free fall time for the central region will be shorter, so the density near the center increases more rapidly. So the density of the center increases more rapidly. Grab my laptop, which I haven't put out yet. No need for the viewer at home to wait for this delay. So expect a jump in the video. Okay, so while we were away, I asked for questions. And basically the questions were along the lines of, wait, so how does this work out? How does every part of the cloud manage to get to the center at the same time? So let's look at that in more detail. So let's consider a parcel that starts out some distance r from the center, and another parcel that starts out at 2r from the center. And let's figure out what the acceleration is at those two locations. How do they compare to one another? So, in other words, what we want to do is figure out how much mass is interior to each radius, versus its distance from the center. So m sub r is going to be 4/3 pi rho times r cubed, right? Density times volume, 4/3 pi rho cubed, 4/3 pi rho r cubed, and m for 2r, mass interior radius 2r, will be 4/3 pi. We're assuming the cloud's of uniform density at all times, well, initially, and then it will always be at all later times. 4/3 pi, different density, but it will always be uniform density if we have a homologous collapse. 4/3 pi rho times 2r cubed, right? So 8 times bigger, 8 times 4/3 pi rho r cubed, right? The acceleration due to gravity is is gm over r squared, right? So gm of r over r squared at r is going to give us equal to 4/3 pi rho r times g, right? 4/3 pi rho r times g. Did I do that right? I'm just doing this off the cuff here. All right, I'm going to divide by r cubed by r squared. And 2r will be gm of 2r over 2r squared. Right? So that'll be, my m of 2r was 8 times 4/3 pi rho r cubed. And now I'm dividing by 2r quantity squared. So I get 2 times g times 4/3 pi rho r, twice as big. So if you're twice as far, the acceleration is twice as big, which I really could have just gotten from this relation right here. In other words, from the beginning. At radius r, the acceleration is g times 4/3 pi rho r. So if you double the radius, the acceleration is twice as big. If you triple the radius, the acceleration is 3 times as big. The acceleration is proportional to your distance from the center of the cloud. And so therefore, if you start twice as far away, your acceleration is twice as big. And as the cloud collapses, it will always be true that a point twice as far from the center as another point has twice the acceleration. So at all times, this parcel that started out twice as far from the center has twice the acceleration of the other parcel. And therefore, its velocity is always twice as big, because the velocity is just the integral of the acceleration. So if at all times the acceleration is twice as big, the integral, which gives the velocity, is always twice as big. That's why all parts of the cloud get to the center at the same time, because your velocity is proportional to how far you are from the center. So points twice as far from the center are always moving twice as fast, so they get to the center at the same amount of time. Does that make sense? That's what it comes down to with the homologous collapse. So to picture it, really all you have to do is say, you're picturing it's like, there's like here's the surface of the cloud initially and halfway out to the surface. At some later time, the cloud has shrunk. How do I draw this surface? If the outer surface is turned into this, what is this surface halfway out to the center turned into? Another surface halfway out to the new surface, halfway out to the surface, I meant to say. Another surface halfway out to the new surface. Maybe I'll draw a dashed line. When the cloud has become that big, how do I draw the dashed surface? Again, halfway out to the whole radius. And so forth. So the whole thing's just shrinking in a uniform way. In a uniform way. If it was a rainbow, red, orange, yellow, green, blue, violet. And each of those layers of red, orange, yellow, green, blue, violet, each of the red, orange, blue, violet, each of those 7 layers, not 8 but 7, because there's no layer, right? If I drew it as a pretty rainbow, and each layer was 1/7 of the radius of the whole cloud, as it shrank, the pretty rainbow that I was drawing, each layer would always, the different colors would be 1/7 of the current radius of the cloud as it shrank. That's what the homologous collapse represents. Now, it collapses faster and faster as it goes, but at all times, the pretty rainbow is just, the cloud always looks the same. It's just that you need a bigger and bigger magnifying glass to make it the same size on your screen, so to speak. You have to increase the zoom factor more and more as it collapses. That's a homologous collapse. Okay? Does that make sense? Visualize that? You're looking, there's something you want to say.
So the particles, they are always speeding up because they always do have an a positive charge.
Yeah. Every part of the cloud is speeding up as it falls towards the center. The collapse is going faster and faster and faster.
But the rate at which it is going faster is decreasing.
No, it's actually going faster and faster. It's not just going faster and faster and faster and faster. It's going faster and faster and faster because as it shrinks, the acceleration is getting bigger and bigger. So, in other words, let's now show this plot of what the collapse not looks like, but a plot that shows how the density and the radius change. Drop the screen here.
It just cuts off and falls onto the floor.
Yeah, it would eventually, it probably like wow.
Do the other one.
Yeah.
Put them all down.
There we go.
Just leave them all down.
Yes, that's right. Yeah. So this is a plot from the book for a homologous collapse. I have a molecular cloud where the initial density is 3 × 10⁻17th power kilograms per cubic meter. Because the free fall timescale is independent of the radius of the cloud, we get exactly the same plot no matter how big the cloud is initially. It's always going to be exactly the same. It only depends on the density. The free fall timescale only depended on the density and g, and the 3 pi over 32 or 32 over 3 pi or whatever it was. So notice that, so this is r over r naught. So at time 0, the radius is the initial radius. For every layer within the cloud, this could be, you could do this for the surface of the cloud, but for every layer within the cloud, the plot looks exactly the same. Notice what happens is initially, the radius is only slowly changing with time, but because the acceleration keeps increasing. It's collapsing faster and faster and faster and faster and faster and faster and faster, and it kind of drops off a cliff by the end here. And so at a finite time, namely, it looks to be about, like 370,000 years or something like that. After a finite time, the radius has become 0. And then here's, this is the logarithm of the density over the initial density. It's going up to infinity because it's turning into a black hole, which isn't what really happens because it becomes optically thick and pressure starts to balance gravity and it slows down and becomes a star. But in other words, if that didn't happen, the density would go to infinity because this is saying it collapses to a point. If it doesn't happen, but that's what this is saying. So, in other words, the idea is that the collapse initially is quite gradual, but you're compacting more and more mass inside of each layer, so the acceleration keeps going up, and so it's so to speak. And then it's, really it's, pressure takes over and starts to balance gravity, and so now let me obey the virial theorem and start having some of this gradual gravitational collapse be converted into thermal energy, and so my core gets hotter and harder and hotter, and so, nuclear fire has been lit and I am now a star. But that's not what we're talking about here, right? We've ignored that last part where that never kicks in and it goes, holy crap, it's a black hole! Except that's not what actually happens, okay? That's the idea with our homologous collapse. And the collapse is initially pretty much homologous, but in a real protostar, pressure kicks in because it eventually becomes optically thick. It starts trapping some of the radiation that it's emitting, and it starts to heat up so that the pressure starts rising. And it's no longer true that gravity is dominating pressure and it's in free fall. That stops after a certain time. Yes?
It's maybe a dumb question.
But then how does like the Big Crunch work? Wouldn't it just form one big star with everything, all the mass?
That's not a dumb question. That's a great question. That's a great question. That's one of the things, because you're anticipating what what we're about to say, which is this seems to imply that you could form a star of any mass whatsoever. That's not what we observe. This is what's known as the initial mass function. It's based on observations here. The dots are observations there. What we find is that, in fact, very massive stars are rare, and low mass stars are much more common. In fact, the sun is, again, you always see this thing, the sun is a small star, blah, 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 because there's much larger stars. This is true. But in terms of mass, the sun is actually in about the 90th percentile. The sun is more massive than about 90% of the stars in the universe.
Go sun.
Go sun, that's right. By far, the most common stars are M dwarfs, ones that are much less massive than the sun, very dim, you can't see them out to very far. Low mass stars form much more readily than high mass stars do under present conditions in the universe. It's thought that when the universe was very young, that was not the case, but let's take the universe as it is now. Low mass stars form much more readily than high mass stars do. So why is that? Let's see if we can understand why a cloud would fragment. Because that's the idea, is that eventually the cloud starts to fragment and form a bunch of stars instead of one giant star being formed out of a large cloud. Why does fragmentation happen? This is our quest to understand, at least qualitatively, why that happens. Notice the initial mass function there is essentially a plot of star formation rate in the galaxy versus the logarithm of the mass, and 0 would be the sun's mass, and so because it's that's in terms of solar masses. So notice and it's a logarithmic scale, so you know it's compressing things a lot. So notice that the peak is at less than the sun's mass. So less massive stars form at much higher rates than more massive stars do. Why should that be? Well, it's not fully understood exactly what sets the star formation, but we can say something that clarifies the picture. So let's do that, shall we? Mute. And send screen back up again. That exercise going across the board back and forth. So our analysis seems to suggest that stars of any mass could form. But in fact, low mass stars are much more abundant than high mass stars. Sun is more massive than about 90% of stars. Why? Because clouds fragment. While forming stars. So you get a bunch of smaller stars instead of one big one. And this is where we should just stop because I can't say it in 3 minutes. And so
Stop really fast.
we'll just, what's it? No, it's not very fast. Okay, so the adiabatic gas law is P equals K rho to the gamma. But P is rho KT over mu mh from the ideal gas law. So the rho KT over mu mh is equal to K rho to the gamma. Or in other words, T is K double prime rho to the gamma minus 1. Since the gene's mass is the 3/2 power of 5 KT over G times mu mh times the 1/2 power of 3 over 4 pi rho c, we have that the gene's mass is proportional to the cloud's density to the gamma minus 1, that to the 3/2 power, times the cloud's density to minus 1/2. Or in other words, the gene's mass goes like the density of the cloud to the quantity 3 gamma minus 4 over 2. And that means that for atomic hydrogen gamma, since it's 5/3, the gene's mass is proportional to the cloud density of 1/2. So what happens is the gene's mass increases as the cloud collapses, and this results in a minimum value for the mass of the fragments. Okay, I guess we covered it.
And that's it.
Yeah.
That one.
Let's say that again slower
Next one.
next time. Yes.
Well, technically, all we have to do is go back and watch the video at a slower pace. And
Yeah, that's right. Exactly. We'll just slow it down. YouTube